so much for coming.
Great.
Take it away.
Thank you for the introduction, Sean. So yes, as Sean said, I'll be presenting on small HVAC heat pump sizing. And actually, I'll be going through 3 different ways of sizing HVAC equipment. I'll be walking through the Energy Pro 7 load calc, which uses the ASHRAE model, the manual J calc, which is the industry standard, and then the passive house calculation. And I'll be comparing all 3. All right, so overview. In this presentation, we'll be discussing small HVAC systems and focus on retrofit sizing for small heat pumps in existing multifamily buildings. We'll go over considerations for sizing small heat pumps, 3 strategies used for sizing small heat pumps, like I said before. We'll be doing an energy modeling, Energy Pro 7, that uses the ASHRAE model, manual J, which is the industry standard, and then passive house method. We'll be comparing all 3 results, and then we'll also be discussing future considerations. All right, considerations and overview for small HVAC heat pump sizing. I believe it's important to understand the context, the existing heating appliance, reason for the retrofit, the tenant demographic. Is it a single family? Is it a large family? Is it a college student? And then also location. Is it a heating climate? Is it a cooling climate? What are the design degree temperatures? Demand versus load is important. Demand is going to be your annual energy usage over the year. We use demand to calculate how much energy that unit is going to save versus the load, which is actually sizing and determining the capacity required to heat the unit. And then also surface temperatures are important. We don't want to reach any dew points on the walls or interior surfaces. And then humidity is another consideration. In the Bay Area, we don't really have to deal with humidity too much, but in other places, they do. Okay, so the building that we're going to be sizing, we're going to size 1 unit. It's a real building in Palo Alto. It's a multifamily building. There are 24 units, 16 1-bed, 1-bath, 8 2-bed, 1-bath. It's 2 stories. In this project, we're only going to be retrofitting the 1-bed units. So there's an existing wall furnace, and we're going to be replacing them with either a mini split or a package terminal heat pump. And so in order to make our lives easier, we typically size for the worst case 1-bed unit. So I'll go over to how to identify that. Instead of sizing all 16, we just pick 1 that we've identified as the worst case. The 1-bed unit area for all 1 bedrooms is 540 square feet. The ceiling height is 8.96 feet. I got this from the building plans that were, this building was built in 1998. So I'm not sure why they use 8.96, but that's what we have. The existing wall furnace for the 1-bed unit, its input is 28,800 BTUs per hour. Output is 20,160 BTUs per hour. And the AFU is 0.68. This is important because after we size it, we're going to see how oversized this wall furnace is actually, Like I said, the building is constructed in 1998, located in Palo Alto, climate zone 4. The ASHRAE design temp is 26 degrees Fahrenheit. This is actually generated from Energy Pro 7. And if you look at the different design temperatures, the 26 degrees is much lower than the manual J design temp and the passive house design temps. This is because no matter for Energy Pro 7, you put in climate zone 4, it's going to find the design temp for climate zone 4. So that's an issue off the bat. I mean, it's never going to get 26 degrees. It's never going to be 26 degrees in Palo Alto. Manual J design temp is 38. Passive house design temps, there's 2 of them, 43.2 and 48. We'll go over why there's 2 of them later in this presentation. All right, so these are our building layouts. On the right, we have our ground floor. On the left, we have our 2nd floor, and this is building A. There are 2 buildings at this property. You can kind of see my takeoffs that I had for this building. And then here we have building B. 2nd floor again is on the left. Ground floor is on the right. And the unit highlighted in red is actually a unit that we determined as being the worst case unit. This is actually interesting because we determined it would be the worst case unit because it has the most exterior surface area, wall, roof. Below it is a unit. And so it has the most exterior surface area. However, when I actually modeled the entire second floor of this property, and the unit above, hopefully you can see my mouse, the unit above was determined to be the worst case unit, even though it had all of this all these south facing windows. And that's because Energy Pro 7 doesn't take into account solar heat gain. So this was the real worst case unit. And so here are bedroom unit layouts. On the right is unit B on the type, and the left is unit A type. We'll go into unit B a little bit more because that's the unit type that we identified as worst case. All right, so now we're going to go through Energy Pro 7 load calc and how to do that. This is fairly straightforward. If any of you have done any energy modeling, I'm sure this is going to be a review.
Well, no, but remember, this is training for other people who haven't, like myself.
So. Okay, great. So like I said, identify worst case unit, most exterior wall surface area. We also wanted to make sure that we had the most southern exposure to windows, where Energy Pro 7 doesn't take that into account. And then we also have, this kind of goes for all modeling or all calculations. We want the envelope details, interior and exterior walls, windows, attic, interior floors, exterior floors, crawl space, slab on grade. And the energy modeling software EP7 uses ASHRAE cooling and heating load calculation manual. I went into the ASHRAE heating load and calculation assumptions and considerations. So it automatically selects your outdoor design temp, which is 28 degrees. Select your indoor air temp, assume 70. This is because Manual J assumes 70, and building code actually requires that a unit is maintained to 70 degrees Fahrenheit for a heating load throughout all weather types. So I changed it to 70. Temperature in adjacent unheated spaces. The ASHRAE heating load calculation actually has separate calculations for each type of adjacent space, whether it's a garage, whether it's a common area, whether it's another unit. And it calculates an air temperature in order to calculate the transmission losses. And so, but in Energy Pro 7, it overrides that and just assumes it's equal to the unit's temperature, which is in this case would be 70 degrees. We need to determine surface areas of exterior walls, interior walls, windows. That was the takeoffs that you saw in the plans. We also want to compute heat losses from basements or grade level slab floors. In this case, we're on the second floor. We have a unit below it, and we're going to assume that it's 70 degrees in that unit as well. And then ACH, we need to measure the air changes per hour, leaks, cracks, exhaust fans, supply fans, wind speed, coverage. EP7 actually has an embedded calculation for your air changes per hour. And it's fairly low. I mean, you guys were talking about earlier, we're talking about 4.5. We'll look at what EP7 spits out. You can put an air changes per hour, but if you do a load calculation, it just overwrites it. So that's something that is not great either. Factors that EP7 and ASHRAE do not consider for heating load is shading, orientation, internal gains, and also because shading and orientation also doesn't include solar heat gain. So that's another gripe. Okay, so we start at the building level. At this point, you just want to have quick names. The most important part about this slide is that you select climate zone 4. The city actually doesn't matter. It's just the climate zone that they take into account. And then we move on to domestic hot water. In typical energy modeling, you need to dial this in. But if you're modeling for a load calc, the water heater doesn't really matter. So you just need something for it to be able to comply. In this case, I did a standard gas, 50 gallons or less. I included that it's a multifamily central system with a pump and a demand controller, but that was I just inputted that just to be safe. Again, HVAC, not a big deal what you input. You're going to be sizing the HVAC, so whatever you put in here isn't a big deal. I just put an electric baseboard because it was the first option that I saw. Now we're getting into stuff that actually matters. Worst case unit. We need to make sure that the zone type is conditioned, occupancy, multifamily. This actually, you can do single family or multifamily. And then year built, it was built in 1998. It's not going to make a difference if you put 2000. So now we need to put in our area, 540 square feet, our winter indoor temp. Default is 68. You have to upgrade it to 70. We have no installed LPD. That is lighting. And because we have no installed lighting, we have no internal gains considered in the load calcs. It is considered when you're doing a cooling calc, but for heating, they actually take that out of the calculation. All right, so now we have our walls. We have our north exterior wall. The orientation is 30 degrees because the building is not exactly dead center to north. We have an existing assembly of R13. If you look to the right, we have our Title 24 standard, which is also R13, and they're giving the U factors. If anyone were to take the inverse of this, you notice that it would actually be R9.8. This is because it's an existing building. Energy Pro 7 is going to automatically assume that the insulation isn't QII or up to QII level. So it's likely that the R value is going to be decreased. So it's actually an R value of 9.8. And so we use that. I use that throughout all my calculations in order to be consistent. So we have our north window, double non-metal clear. That's just it's a vinyl window. We don't have any window details in the plans. We just have the sizes of the windows, and we know that they're double pane vinyl because we've been out at the properties. So we just use the defaults, which is a U factor 0.55 and a solar heat gain coefficient of 0.6. Again, the solar heat gain coefficient isn't going to be taken into account in this model because you're doing heating load, and Energy Pro 7 does not take into account the solar heat gain through the windows. And also, we don't need anything inputted for the overhang for the same reason. There's no solar heat gain, so there's no shading. Interior wall, R13, that's based off the plans. And if we actually go back to this drawing, we have an interior wall to the unit south, and we have a small interior wall to a common area. This is actually a tower. I'm not sure why they included that in the design, but it goes about another floor up past this unit. And so that's another interior wall, but it is conditioned. And then we also have our roof. Our roof is R30. It's the square footage of the unit, and its orientation is 30. That's basically it for the roof. And so in Energy Pro 7, you hit calculate, it spits out all this information. You can hit print, and you can print a report. This is the page of the report that's most important, and it tells us our heating load is 6,786 BTU per hour. Now this is pretty much the easiest way to get to a heating load. If anyone has ever used Energy Pro 7, you know how quickly you can model this. The biggest kind of time waster, or the thing that takes the most time, is going to be your takeoffs. So that's measuring your windows, measuring your walls, that sort of thing. All right, so now we're moving on to manual J load calculations. Manual J heating load calcs. So I use the abridged version of the Manual J 8th edition. Some assumptions that Manual J uses is windows and glass doors shall be equally distributed around all sides of dwelling units. So keep in mind, this is the industry standard. So if you do not get credit if you have, well, it also doesn't take into account internal gains or sensible gains from fenestration. So you don't have solar heat gain, but you don't get credit if you have a huge south-facing window that's going to be gaining heat all day. They don't consider that, and they actually distribute it around all dwelling units. And then also, dwellings shall have adequate exposure diversity. So this is also with regards to shading. And these two assumptions also are for the cooling load. So if you have a huge south-facing window that's going to increase your cooling load, it's not going to take into account. It's going to distribute that area of window for all four sides. And then a bridge version of the Manual J 8th edition is available online if you want to use it. Contractors use it all the time. As I said, it's the industry standard. So this is kind of in what is the version Manual J 8th edition. We start out with our windows. Again, we just put our windows in. It has a heating U value of 0.55. The cooling HTM is for the cooling load, and that you look that up in a table, and it kind of gives you the sensible heat gains for the cooling load. It does not take that into consideration for the heating load. And then you have window input. You don't actually put in your linear square footage of your window. You only put your height. And so this is typically only used for cooling load, but I inputted it for heating load because you won't actually get a number if you put in the heating load. And I believe based off the assumptions that the windows are distributed evenly across each orientation, I believe they do some sort of internal calc and assume a window size. And so another thing to point out is you don't get to choose whether your window is facing east or west. It's both east and west are grouped together. And in this case, for the height, I used a weighted average, and the overhang distance, I used a weighted average for both. And it's interesting that you can't choose east or west. I would assume that you would be able to choose that orientation because, I mean, you get a lot of heat gain in the west, in the east. No, sorry, in the west. More often in the northern hemisphere. So that's something interesting too, that they make kind of behind the scenes assumptions. And then you have your exterior wall, your U value, same as before, 0.12. Your interior wall is again R13, which is derated to R9.8 based off Energy Pro 7, which again is 0.102 for U value if you take the inverse. And then you have your roof / ceiling input, which our roof was R30. If you take the inverse of 0.031, it's actually R32. I'm not quite sure why Energy Pro 7 does this. I believe they increase the R value, maybe because you get some air barrier, because typically you have a vented attic. So they increase the R value because of the air barrier. You have construction details that also increase the R value. And I think also most attics are loose batt, loose fill fiberglass. And so loose fill fiberglass is a little bit easier to achieve QII than actually having batt. So then we put in our floor input. Again, this is a partition floor between a unit, between two units, and it is actually R13 again, which was derated to R9.8. Now we get into ventilation losses. This is where it gets a little interesting. Envelope leakage is semi-loose. It's fairly subjective. I tried to look into what they define as semi-loose, and I wasn't quite sure. It didn't make much sense to me. Number of fireplaces, it has to be at least one. I mean, if you're modeling a building that doesn't have any fireplaces, you just have to assume one. And then you input your heated and cooled floor area, and then above grade cubic feet, and it spits out infiltration losses of 955 BTU per hour. And also, if you look at the next, it has internal gains. This is for the cooling load again. The Manual J assumes per bedroom there's one person, and then they add another one, so that's why you have occupants of 2. And then appliances is 1200 or 2400 BTU per hour, and that's just subjective. Whoever is the designer or the load calc person.
Can you pause on that for just a moment?
Yeah.
So internal heat gains, and this is for low rise or high rise software?
It's residential. It's
low rise.
Sorry?
You mean low rise, or do you mean the residential component within the high rise?
It's just I believe manual J doesn't actually decipher between low rise and high rise.
Oh,
It's general across all residential. Low rise and high rise is within. So manual J is not specific to California, and then
oh.
low rise and high rise is only Energy Pro, or CBEC Res versus CBEC Com.
Well, before I dig into the question of, well, within the appliance, 1200 BTUs per hour,
Mm-hmm.
I can imagine incandescent lights versus LED lights,
Yeah.
or better refrigerators versus, I can just imagine all these variables. And I'm wondering, how much of a difference does it make? Like, really, is it worth digging into that with 1200 here versus the other values that are being brought to bear, like the energy of the compressor?
Yeah. Well, actually, at the end, we're going to look at the values of all three for internal gains. And so it actually makes quite a big difference when you're doing a small unit like this. And
Oh,
when we do our modeling, we also make sure to include losses by adding LEDs. So if we're switching from incandescent bulbs to LEDs, we actually take a hit on the heating side of things because now we don't have that excess heat. If we're installing if there's existing cooling, it's pretty negligible, but it's still a hit that we have to consider. But yeah, you are correct about you do receive a hit when you install LEDs versus incandescents, but the load is something that we should consider, internal gain. And we'll get into that on the passive house side.
okay. Continue. Sorry. Thank you.
No worries. All right, so this is the load summary that spits out for manual J. And so what I really like about this is that it gives you percentage of heat loss. So if you're designing a building, if this is new construction, I rarely work with new construction, but if you were, you can kind of look and see, okay, well, our total area of our windows is only 121, and our heat loss is 37.46%. So we could use a better windows, and that would significantly reduce our heat loss, overall our transmission losses. And I mean, right now we're assuming 0.55 U factor, and Title 24 is 0.32. I've seen U factors as low as 0.25. So that's really not too far-fetched to increase the windows, and that may be a recommendation. Increase the efficiency of the windows. That may be a recommendation that we make to this property. All right, now we're on to the passive house load calculation. So this is going to be, the past two have kind of been like abstract. You use a calculator. They really hide all the calculations behind the scenes. For the passive house load calculation, that's not the case. And I actually did this by hand. And so we can kind of go through this. So passive house method. Again, we have heating demand and heating load. It's important to differentiate these. Quantity of energy over 1 year is heating demand. You should use that if you want to calculate your savings, of how much energy you're going to save by installing more efficient equipment. Heating load is the power required to maintain a comfortable temperature. We use the heating load calc to size the heater. And there is two cases that we have to take into consideration because passive house includes solar heat gains and it includes internal heat gains. This just really affects the solar heat gains. We have a case one, which is clear and cold, which is 43.2 degrees Fahrenheit. So it's a little bit colder. However, you're going to get a little bit more solar heat gain into the unit. And then case two is your cloudy and milder climate, which is 48 degrees. Again, it's going to be a little bit warmer. However, you're not going to have the same solar heat gain coefficient. And to be consistent through all three methods, we include a temperature set point in unit as 70 degrees Fahrenheit. The floor to ceiling height is 8.96. And the big difference is that this includes solar heat gains and includes internal heat gains. Okay, so energy balance equation for heating load. So this is kind of like overall, we have our peak heating load, we have transmission losses, we have transmission losses through linear thermal bridges, transmission losses through point thermal bridges, ventilation losses, solar gains, and internal gains. And so these transmission losses through thermal bridges and point thermal bridges, Energy Pro 7, ASHRAE, and Manual J do not consider these. They're pretty small, so you could consider it negligible, but what I really like about the Passive House is that it's very specific and it's very detail oriented. And so you can really size this unit, really dial in the sizing.
May I ask briefly there, when you say really small, is that less than 10%, less than 20%, less than 5%?
Less than 15, or sorry, less than 10, less than 10. I mean, the transmission loss for this, well, we'll get to it, but the transmission loss for this was around 4,000, and the linear thermal bridges and the point thermal bridges was around 20. But I use an assumption for that. Thermal bridging, we'll get to the thermal bridging in a second.
And the solar gains, I apologize, but to get a sense of that, this is a new thing compared to the previous examples. So solar gains, what kind of contribution does that make a difference to this overall equation?
Solar gains are important. They reduce your heating load quite a bit. Especially in this case, there's a lot of shading. But the idea of Passive House is that you can design a house that utilizes solar gains, and you can even utilize thermal mass in order to create the most energy efficient house that you can.
Thank you.
Yep. And we'll go over each one of these individually. So transmission losses, you have your transmission losses equals surface area times the inverse of the R value, which is equivalent to your U value. Utilization factor. Utilization factor is typically 1, but it's basically when you're going to utilize. So if we're calculating the cooling load, and you had a thermal mass, and you had heat coming into your building, and through solar gain, and you actually have a utilization factor because you want to take that heat, heat up the thermal mass, and then at night it's going to reduce your heating load. But when you're calculating heating load, it's typically 1, and then you have your delta T, which is your indoor temperature minus your weather condition 1 and weather condition 2. So those were the cases that we had before. And you have to do this for every single surface area. So you have your exterior walls, your interior walls. In this case, we assume that the interior walls, the adjacent spaces were the same temperature. So those actually zero out. But if you weren't to do that, you'd have to do each one. And then also your floor area. And you actually compare this. You have to do this. You have to multiply that by 2, because then you do it for each temperature case. So the cold and clear, and the cloudy and moderate temperature. And so now we're moving on to transmission losses, calculation from thermal bridging. So you have your your linear thermal bridges. These are typically like your studs, your corners. Kind of what Passive House really drives is continuous air barrier, continuous insulation. And so when you have points where you have a break in your insulation, like a stud, or in this case, we're looking at a wall/floor junction, you actually have increased heat flow. So you see on the point at the figure at the bottom, you see the heat flow coming through there because you have a break in your insulation. And then we also look at point thermal bridges where our single points, they don't have the same length or the same, they're literally just points. Like that could be a nail, that could be lots of things, a connection. They don't have a distance. They don't have distance factored into it, where linear thermal bridges do, and you have to multiply them by the distance of the thermal bridge. So for this case, oh, sorry, I forgot one thing. If you were to actually calculate the thermal bridges, you would want to use software to do so. And Lawrence Berkeley National Laboratory therm software was recommended by the Passive House Academy. And I did not do that for this project. Through the Passive House manual, they give an example of ranges of thermal bridges, and the kind of one of their worst case or bad thermal bridges was 0.25 BTU per hour. And so I used that as our linear thermal bridge value and our point thermal bridge values. And the figure on the right, it shows all the different thermal bridges in this unit. So at each window, you have a thermal bridge. At each point where there's a corner, you're going to have a thermal bridge. At each stud, I didn't draw that out because this would just be a huge red line, but at each stud, you're going to have a thermal bridge. Yeah. So ventilation losses calculations, you want to take your ventilated volume times your effective air change rate times the heat capacity of air times the indoor temperature minus the temperature weather condition 1 and 2. And so again, you have to do this for both weather conditions. The ventilated volume is basically the volume of your unit. In Passive House, sometimes you take out furniture or unconditioned spaces. In this case, we assumed that just the ventilated volume was the volume of the unit. Effective air change rates, I'm not going to go into how to calculate that. We have an internal air change rate calculator here at AEA that takes into account where the building is located. Is it exposed? How exposed it is? Is it? What are the CFMs of the exhaust fans? What are the CFMs of the supply fans? That sort of stuff. Okay, finally, we have our solar heat gain calculation. And this is reduction factor times solar heat gain coefficient times the gross area of the window. And you have to do this for, going back to the different cases, because one case is cloudy and mild temperature, and the other case is sunny but colder, you have different, oh, sorry, I forgot to add the G, but that is basically your solar gain. And so you have a different solar gain from the north, east, west, each orientation, and you have a solar gain, a different solar gain for each case. The reduction factor is going to be the same for each case, but however, it's going to be based off of, is there dirt on the window? We assume 0.95, which is a very low reduction factor. Is there shading? In this case, if you look at the unit that we're doing, there's a large redwood tree right next to the biggest window, and so there's high shading. We have a high shading reduction factor, and then it also includes. You also have a reduction factor because the sun isn't hitting it directly. There's like a horizontal. It's not hitting the window directly, so we have a reduction factor for that as well. And then again, we have our solar heat gain coefficient, which is it was, I think, 0.67 was our solar heat gain coefficient. Finally, we're on to internal heat gains. So for internal heat gains, we have Pi equals Qi times A. So A is your treated floor area, Qi is your specific internal gains. I'm not quite sure how Passive House calculates this and why they use specific, because basically when you get to specific, it means it's divided by the square footage. For this example, heat gains from ASHRAE appliances assume 1600 BTU per hour. For manual J, they assume 1200 or 2400 BTU per hour. For this example, I chose 1200 BTU hour because that is the smallest value. And then also for internal gains from people. ASHRAE and Manual J both assume 230 BTU per hour per person. ASHRAE and Manual J assumes one person per bedroom plus one, and I conservatively chose one person. So in this case, ASHRAE and Manual J would assume two people. But since I know that from reviewing these assumptions that ASHRAE and Manual J both make, I'm assuming that 1200 is fairly conservative for calculating a cooling load. So I kind of tried to level that out by reducing the amount of people by making it one person. So I calculated for case 1 and case 2 the transmit. So if we look at the transmission losses for the clear and cold day, it's a little bit higher, which makes sense than case 2 because the temperature is colder outside. Ventilation losses, this is interesting. Ventilation losses are very high compared to the Manual J and the ASHRAE version. Solar heat gain calculation, we got 153.4 versus a cloudy and mild day, 48.9, which is about a third. Also to consider, we also have to consider that this was the worst case unit. So we chose this unit because it was heavily shaded. There was no southern facing windows. The windows that they did have either had a large overhang or a giant tree in front of them. So we picked, so the solar heat gains are much smaller than another units. Internal gains are going to be the same. Peak heating load is 4,676.7 for the clear and cold day. Cloudy and mild, peak heating load is 3,711. So in Passive House, you do these two different methods based off two different cases of clear and cold and cloudy and mild, and you choose whichever one is the highest or the worst case, you pick that one for your heating load. So in this case, our peak heating load used to size the small HVAC system is 4,676.7. All right, so now we're going to go through the comparison of all three methods and the conclusion and future considerations. So comparison of three sizing methods. Transmission losses are less in the Passive House, and so that's only transmission losses. That does not include any internal heat gains or solar heat gains. I believe that's just because Manual J and Energy Pro have, or ASHRAE have assumptions that are embedded in the programs or the workbooks that they've locked, and so the transmission losses are greater. And also it's probably mostly caused because the design degree temperatures are so different. Energy Pro 7 ASHRAE assumed 28, Manual J assumed 38, and Passive House was in the 40s. So that's probably why you see a less transmission losses. Ventilation losses in Passive House, it's extremely higher. Energy Pro 7 and Manual J, they don't increase the, Passive House increases your air changes per hour. They multiply it by 2.5 because they're assuming that on a cold day, you're gonna have the most wind. We're gonna have high wind velocities, which is gonna create a larger differential in pressure between the indoor air and the outdoor air. And so you're going to have a higher rate of leakage because of that increased pressure differential. So they ask you to multiply whatever air changes per hour that you got by 2.5, which you can see has a dramatic increase on the ventilation losses. Your solar heat gains, there are none for Energy Pro 7, there are none for Manual J. For Passive House, it's 153. And then internal gains, there are none for Energy Pro 7, 0 for Manual J, and 1430 for Passive House. And so these peak heating loads that we calculated are 6,786 for the Energy Pro 7 ASHRAE method. Manual J is 5,700, and Passive House is 4,676.7. And I'd like to point out how much lower these values are than what the existing wall furnace is. The existing wall furnace is 20,000 BTUs per hour. These are significantly less, and so we can not only can we install a electric clean heating device that's higher efficiency, we can also install it at a much smaller size or a much smaller capacity, which would be significant on the energy efficiency side. So conclusions, most or all HVAC systems are oversized. The existing BTU per hour capacity of the furnace was 20,160 BTU per hour. Each sizing method has its own drawbacks. Passive house method is the easiest to manipulate and make it more accurate. Energy Pro 7 method, potential to oversize heating appliance, but not by much. And compared to what the existing unit is, it's still a win if you're putting in a 6,000 BTU heating appliance. And so increased tenant comfort using different strategies than increasing capacity. A lot of cases, we're taking these large wall furnaces and putting them into properties where the tenant has been used to just turning on a wall furnace and their unit is really hot already. So we a lot of times use transfer fans to pull. So say the unit is the head unit or the package thermal heat pump is in the living room, and you have your door closed and you're asleep and you want to keep your bedroom cool or your bedroom hot. You can have a transfer fan that fits into the stud that pulls heat from the living room into your room. Ceiling fans, those are great to circulating heating air, hot air as well, or cool air. Also for cooling load, you can get away with putting in a ceiling fan to lower your cooling load. Just creating a draft can make people feel more comfortable. And then the Quanda effect, this is the reason why most head units for mini splits are placed on the top or near the ceiling. The Quanda effect is if you have an airstream getting pushed out of a fan, or in this case it would be a head unit for an HVAC system, they tend to kind of glide across and stick to a flat surface. So by putting the mini split on near the ceiling, it actually distributes the heat a lot more efficiently than if you put it lower, because it's going to kind of spread along the ceiling and actually spread around the unit. And then another thing to consider is smart thermostats. A lot of these new package terminal heat pumps, they are Wi-Fi enabled, and so by losing capacity, you're going to decrease how quickly these units will heat up your apartment. So if you have a savvy tenant who connects their package terminal heat pump to their phone via Wi-Fi, they can actually preheat their apartment. There are smart thermostats that connect to. They only work with ducted systems. So that'd be like in our case a ducted heat pump. They can actually sense when you're home. They use your phone, or they have an occupancy sensor, so they only turn on when you're home. And you can actually they can program a schedule too, so that they heat before you get home, so your house is nice and hot when you get there. Future considerations, I like to start doing some cooling sizing. Here in the Bay Area, cooling isn't that, there isn't that much demand for cooling, but as we know, it's going to be a bigger and bigger demand. And so, I mean, right now, most of the apartments we do are wall furnace retrofits, or just furnace retrofits in general. So by adding cooling, it's pretty low consideration of the size or the capacity of the cooling unit from our end, because it's going to be better than what they had before. Oversized AC issues, relative humidity. If you have an oversized air conditioner, you could lower the relative humidity of your unit. And if you've ever been in a building that you're constantly getting shocked every time you touch a piece of something that's metal, it's probably because they have an oversized air conditioner that's drying out the air and increasing the static electricity of the building. Undersized AC issues, you can increase the relative humidity. So this is in cases where you have a property that is in a humid climate. You have to be really conscious about that. You need to size the unit properly in order to lower the relative humidity. I think the ASHRAE kind of sets the standard at 50% relative humidity. And also, if you have an undersized AC you're going to decrease tenant comfort. Ventilation, ACH required to provide fresh air. This is just something to consider. In passive house, you need to, the goal is to have 0.06 air changes per hour. And so you need to make sure that it's mechanical so that you can control it and provide enough fresh air into the unit. I'd also like to look at the manual J unabridged version, see what kind of things I can, see what kind of parameters I can change there. Hopefully a lot more than the abridged version, which I assume is the case. And then I'd also, in the future, would like to start modeling thermal bridging for the passive house method. All right, and that's me. Do we have any questions?
Woo! Nicely done, Jack. That was highly technical. You absolutely lived up to my expectation. Thank you for being an engineer.